Good morning, dear students. I am Dr. Jyotirmayi from the Department of Chemistry. Today, I would like to discuss about two important terpenoids, namely gingiberine and farnesol. In the last class, we have discussed about terpenoids, what are terpenoids, how the terpenoids are isolated from the plant sources, and what is the classification of terpenoids, and we have discussed about the general methods of extraction of terpenoids. Today, we shall discuss about two important terpenoids which are having very good biological importance. First of all, we will discuss about the structure and synthesis of an important terpenoid, that is gingiberine. And we will also discuss about another terpenoid that is named as farnesol. So today's our aim is to discuss the structure and synthesis of gingiberine and the structure and synthesis of farnesol. Coming to the first terpenoid, that is gingiberine. Gingiberine is a monocyclic sesquiterpene. Mono means single or one. Cyclic means it is having a ring structure. Sesquiterpene, that is, in the last class we have discussed about the classification of terpenes. So the terpenes are named as terpenes based on the fundamental unit, that is the presence of the isoprene unit. Based on the number of the isoprene units, they are named differently. So what is isoprene unit? Isoprene unit means C5H8 unit. So based on the number of C5H8 units, the terpenes are divided into different categories. In that, gingiberine comes under monocyclic sesquiterpene. This is obtained from ginger. We know ginger, that we call it as alum. So which comes from Zingiberene officinale, that is the botanical name of the compound. So coming to sesquiterpenes, what are sesquiterpenes? Terpenes that consists of 3 isoprene units. So the terpenes containing 3 isoprene units are named as sesquiterpenes. And the molecular formula is C15H24. As we have already seen, isoprene unit is C5H8. As gingiberine contains 3 isoprene units, the molecular formula comes up to 315H24. And another thing to be remembered is gingiberine is a hydrocarbon, which contains only carbon and hydrogen. Some of the terpenes also contain oxygen, whereas gingiberine does not contain oxygen. Only carbon and hydrogens are present, so it is called as a hydrocarbon. It can contribute to 30% of essential oils in ginger rhizomes. Rhizomes means the roots. So usually the roots move downwards, whereas in the case of ginger, the roots spread horizontally. We can see ginger, the roots spread horizontally. So they are called as rhizomes. From rhizomes, that is the roots of ginger, will get the oil. And this is the compound that gives ginger its distinct flavoring. So because of the presence of this terpenoid or terpene, gingiberine is having a definite flavor and a definite odor. Next, coming to the biological importance of gingiberine. As we already know, ginger that comes from Zingiberene officinale is one of the most widely used natural products consumed as a spice. We all know, everybody use ginger. This ginger can be used either in the vegetable curries as well as non-vegetarian curries. Usually we use more of ginger as a spice in non-vegetarian foods. And very important thing is it is used as a medicine. Ginger is used as a medicine for treating nausea, dysentery, heartburn, diarrhea, loss of appetite, infections, cough, bronchitis, and many more. Nowadays, because of the corona pandemic, we started using more quantity of ginger because of all these medicinal purposes. Then, coming to the plant, here you can see the Zingiber officinale. This is the plant, this is the root. The root moves horizontally and the root is called as ginger. Then here we can see the structure of gingiberine. The molecular formula of gingiberine is C15H24. Here we can see a cyclohexane ring. And in the introduction, we have seen that it is monocyclic. Here you can see one ring, and the ring is having two double bonds which are conjugated. That is, they are alternate. Here, single bond, double bond, single bond, double bond. They are conjugated. And here, this carries a methyl group. Just opposite to methyl group, opposite is called as para position. The para position carries the side chain. The side chain contains one single bond and ends with dimethyl groups. There are two methyl groups. So this is the structure of gingiberine. Then coming to the structural determination of gingiberine. The structure of gingiberine can be derived with the help of the chemical reactions which the compound undergoes. Here we can see gingiber or gingiberine undergoes ozonolysis. What is meant by ozonolysis? Ozone plus lysis. Lysis means breaking down. So here the molecule breaks down when it is exposed to ozone. This reaction is called as ozonolysis. So the breaking of the molecule into simpler units by exposing or by passing ozone is called as ozonolysis. As we have seen in the previous slide, here we can see number of double bonds. Two double bonds are present inside the ring and another double bond is present outside the ring in the side chain. Whenever there are double bonds, when it is exposed to ozone, the oxidation takes place at the double bond. The bond breaks here, one oxygen adds to this carbon and another oxygen adds to this carbon. Same is the case. Here also the bond breaks, oxygen adds to this carbon and another oxygen adds to this carbon. Same here also you can see the formation of the carbonyl group. Thus, on ozonolysis, you can see that gingiberine on ozonolysis gives three different products. Here you can see acetone. Here you can see dicarboxylic acid. Di means two carboxyl groups are there. And it is a keto-carboxylic acid, having a keto group and carboxylic acid. So these are the three products that are obtained by the ozonolysis of gingiberine. So the same similar products are also obtained from some other compound called as bisabolin. So bisabolin on ozonolysis gives similar compounds, which indicates that bisabolin and gingiberine are having similar structures. So if you know the structure of bisabolin, we can give the structure of gingiberine. So based on these facts, we can give structure for gingiberine. So coming to bisabolin, based on the position of the double bond, three types of bisabolins are there. Alpha bisabolin, beta bisabolin and gamma bisabolin. Here if you see the double bond is here, in all the three cases you have the double bond in the cyclohexane ring. The position is the same. Another double bond is here. So the position is the same for all the three compounds. So these three compounds differ in the position of this double bond. Here the double bond is here and the double bond is here and the double bond is here. So based on the position of the double bond, They are named as alpha bisobolin, beta bisobolin, and gamma bisobolin. So we can call them as position isomers because they differ in the position of one double bond. So based on these facts, we can give this particular structure for the carbon skeleton of bisobolin. So six-membered ring is present, cyclohexane ring is carrying a methyl group. In the exact para position, there is the side chain having the double bond and two end methyl groups. So from other reactions, it was found that gingiberine contains 3 double bonds and 2 double bonds are conjugated, and it is monocyclic in nature, homoannular diene. So it is found to contain 3 double bonds. So in this case, we got the position of one double bond only. So we need to find the position of the other double bonds. And second thing is, 2 double bonds are conjugated. 2 double bonds are conjugated. That means they are present alternately. And the third one is, it is monocyclic. We already know that there is a 6-membered ring. And the last one is very, very important. It is homoannular diene. That is, it is a diene. Diene means having 2 double bonds. And these 2 double bonds are present in the same ring. That means we came to know that there are 3 double bonds. 1 double bond is present here. The other 2 double bonds must be present in the cyclohexane ring. That's why it is called as homoannular diene. Homo means same. Annular means ring having 2 double bonds. Based on that, we can give 3 different structures for gingiberine. So the double bonds may be present like this, or they may be present like this, or they may be present like this. Based on the synthesis, the structure of gingiberine will be confirmed. Finally, we can say that gingiberine is 2-methyl cyclohexa-1,3-diene, in which a hydrogen at the 5th position is substituted by a 6-methyl hept-5-ene-2-yle group. So this we can clearly see after looking into the structure. So it is a sesquiterpene found in the dried rhizomes of Indonesian ginger, Zingiber officinale. As we have already seen, rhizomes are the horizontally growing roots. And we can say that it is sesquiterpene. That means it is having 3 isoprene units and it is having 1 ring, cyclohexadiene. 6-membered. Hexa means 6-membered. Ring, cyclo means ring. Diene means 2 double bonds. So there is a 6-membered ring having 2 double bonds which are conjugated. Now coming to the structure, we have seen that gingiberine is 2-methyl cyclohexa-1,3-diene. So here, if you see the cyclohexane ring, this is cyclohexa and it is having a methyl group in the second position. If this is the first carbon, second position it carrying methyl group. In the first position there is 1 double bond, 1, 2, 3. In the third position there is another double bond, and in the 5th position there is a substituent. Starting from here, 1, 2, 3, 4, 5. Second carbon is carrying the methyl group and 5th carbon is carrying the side chain. So the side chain is 6-methyl hept-5-ene-2-yle. So here you can see 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 and 7 carbons are there. That's why it is hept. 2-ene, that is, 5-ene, that is in the position of 5th. There is a double bond. So first bond, second, third, fourth, 5th. So 5-ene-2-yle. So second position there is the methyl groups and another methyl in the 6th position. Here you can see another methyl group. This is the name of gingiberine. So finally we can say that gingiberine is 2-methyl. So we start from here. This is 1, second methyl, and it is cyclohexa. So cyclic ring with 6 carbons. 1,3-diene, first position, second, third. First and third positions are having double bonds. And at the fifth position, there is side chain. Side chain containing 1, 2, 3, 4, 5, 6, 7 carbons. And it is having a methyl group in the sixth position and a double bond in the fifth position. So this is the structure of gingiberine. Then coming to the synthesis of gingiberine. So gingiberine synthase is an enzyme found in ginger rhizomes, and it converts farnesyl diphosphate into gingiberine and diphosphate in a single enzymatic reaction. So we are discussing how gingiberine is synthesized in the plant. So in the plant we find farnesyl diphosphate. This is the structure of farnesyl diphosphate. This changes into gingiberine and diphosphate. It breaks down into gingiberine and diphosphate in the presence of an enzyme that is called as gingiberine. So in the presence of gingiberine synthase, the ginger rhizomes, which contains farnesyl diphosphate, converts into gingiberine and diphosphate. So the plant itself contains farnesyl diphosphate, which breaks down into gingiberine and diphosphate in the presence of an enzyme called as gingiberine synthase. That is about the synthesis of gingiberine. Then we'll proceed to the other terpenoid, very important, called as farnesol. So what is farnesol? Farnesol is also a sesquiterpene. So what is a sesquiterpene? Just now we have discussed. The terpene containing 3 isoprene units comes under sesquiterpene. That's why farnesol is a natural 15 carbon organic compound, which is an acyclic sesquiterpene alcohol. This is acyclic. That means there is no ring structure. It is a straight chain compound, but it contains alcohol group. So just now we have discussed about gingiberine, where it contains only carbon and hydrogen, and it is monocyclic sesquiterpene, whereas farnesol is completely different. Even though they have the same number of carbons, gingiberine is monocyclic, one ring is there, farnesol is acyclic, no ring. Gingiberine is sesquiterpene, whereas farnesol is also sesquiterpene having one alcohol group. That means we can see one oxygen that is present in farnesol. So farnesol is also a colorless liquid. It is especially used in lilac perfumes. We have already discussed that terpenoids are famous for specific odor. Because of the pleasant odor farnesol is having, it is used in the synthesis of lilac perfumes. And very, very important thing is farnesol is a natural pesticide. So this is used as a pesticide for small organisms like mites and is a pheromone for several other insects. To kill insects on pests, that is the plants, it is used as a pesticide. The main purpose of farnesol is it is used as a pesticide. Coming to the structure. Farnesol molecular formula is C15H26O. Just now we have discussed about gingiberine, where the molecular formula is C15H24, whereas for farnesol it is C15H26O. So this is supposed to be the structure of farnesol. We will discuss the structure in elaborate later. Then coming to the source of farnesol, where farnesol is present, in which plant we can find farnesol. As we have discussed about gingiberine, gingiberine is present in ginger plant. So similarly, where farnesol is present, you can get farnesol from so many plants like rose, neroli, balsam, musk, lemongrass, citronella, tuberose, cyclamen, etc. Many of the plants contain farnesol. So here I would like to give 2 important examples which we use regularly in our kitchen. So from cumin seed, that is Jilakara, we will get Farnesol. Similarly, from cinnamon, that is from Chekka, we will get Farnesol. So what is the biological importance of Farnesol? So Farnesol is very, very important because of the medicinal purpose. It is used in cancer therapy. It is used in obesity treatment for weight loss. It is used as anti-inflammation. It is used as a pesticide. It is also used in cosmetics, as I have already mentioned. It is used as a lilac perfume, and it is also used in nano formulations. Then coming to the structural determination of farnesol, that is, we came to know the molecular formula that it is C15H26O. There are 15 carbons, 26 hydrogens and 1 oxygen. So we have to find out where the oxygen is present, how the carbons are arranged, whether they are arranged in a straight chain or not, how many double bonds are there, if double bonds are there, where the double bonds are present. All these things can be determined with the help of the structural elucidation. So in structural elucidation, we allow the compound to undergo various reactions. Based on that, we can come to a conclusion about the structure of the compound. Coming to farnesol, here we take farnesol, allow it to undergo oxidation with chromic acid. Chromic acid is nothing but we will get chromic acid by treating potassium dichromate in the presence of concentrated sulfuric acid. So in the presence of chromic acid, usually the compounds undergo oxidation. The oxidation takes place at the hydroxy group. So here we are discussing about farnesol. The name itself says, the name ends with OL, all means there is one hydroxy group. So whenever there is a hydroxy group on oxidation, if it is a primary hydroxy on oxidation gives aldehyde. So farnesol on oxidation with chromic acid gives farnesol, that is the alcohol is converted to aldehyde. This farnesol is allowed to undergo treatment with hydroxylamine followed by acetic anhydride. Usually, the carbonyl compounds undergo treatment with hydroxylamine to form a compound called as oxime. As farnesol is aldehyde having a carbonyl group, reacts with hydroxylamine. So oxygen from here, hydrogens from the nitrogen moves out in the form of water molecule. You can see the formation of C double bond and OH, which is called as oxime. This oxime, on treating with acetic anhydride, undergoes dehydration, removal of water takes place. So a triple bond is formed between carbon and nitrogen. So a cyanide is formed. Thus, farnesol, that is the aldehyde, on treating with hydroxylamine forms the oxime. Oxime on treating with acetic anhydride undergoes dehydration to form a cyanide. So this on treating with potassium hydroxide, that is a base followed by acid, gives two different products named as farnesenic acid and geranyl acetone. So the cyanide on treating with base followed by acid gives two different products, that is farnesenic acid and geranyl acetone. Based on the structures of these products that are formed, we can come to a conclusion about the basic carbon skeleton of farnesol. As we know the structure of farnesenic acid and geranyl acetone, so this carbon skeleton might be present in farnesol. That is, the second carbon must be carrying a carbonyl group, and from the other end there must be a double bond, and this should be in the form of a straight chain. In between there is a methyl group present on the carbon atom. Based on that particular reactions, we can give this particular structure for farnesol. Thus, we can say that farnesol is a farnesene sesquiterpenoid, that is dodeca 2,6,10 triene substituted by methyl groups at positions 3, 7 and 11 and a hydroxy group at position 1. So, dodeca. So, 10 carbon atoms are present in the straight chain. In between, there are 3 double bonds at the second position, 6th position and 10th position. So, you can see from here, second position, this is second, third, fourth, fifth, sixth, 7th, 8th, 9th and 10th. Second position, there is a double bond. 6th position, there is a double bond. 10th position, there is a double bond. And at the end, there is the hydroxy group that is present. And here, it is carrying 3 methyl groups at the third position, 7th position and 11th position. So, here you can see a third position methyl group, 4th, 5th, 6th, this is 7th, 8th, 9th, 10th and 11th, there is one methyl group. So, finally, we can say that farnesol is farnesene sesquiterpenoid, that is dodeca 2,6-10 triene, that is there are 3 double bonds at positions 2nd, 6 and 10, substituted by methyl groups at 3 positions, 3rd, 7 and 11, and a hydroxy group is present at the first position. That is the structure of farnesol. Then coming to the synthesis of farnesol, how it is synthesized. Here we can see a compound called as nerolidol. This is nerolidol. From nerolidol, we can synthesize farnesol. So here the reaction is a single step reaction where nerolidol undergoes allylic rearrangement. Allylic means there will be a change in the position of the double bond. Automatically the functional group shifts from one position to the other position. So if you see here, this is nerolidol. The double bond is present at the end. First position there is double bond. In the third position there is the hydroxy group. During allylic rearrangement in the presence of the acid, the double bond shifts to this position, the hydroxy group shifts to this position. That's why if you see the end, the double bond changed from first position to the second position, from here to here, and the hydroxy changed from third position to the first position. Thus, nerolidol undergoes allylic rearrangement. The reaction takes place in the presence of acid to form a product known as farnesol. This is the synthesis of farnesol. Thus, let us reflect on all the topics that we have discussed today. So, what is gingiberine? We have discussed about 2 important terpenoids, gingiberine and farnesol. So, what is gingiberine? Gingiberine is a monocyclic sesquiterpene, that is, it is having a single ring and 3 isoprene units. The molecular formula is C15H24. It says that it contains only carbon and hydrogen, no oxygen. So, here it is having a single ring, which is a 6-membered ring. This carries 2 double bonds which are conjugated, and this is having methyl group. So at the para position to the methyl group, we can see the side chain. The side chain carries a double bond and ends with 2 methyl groups. This is the structure of zingiberine. Coming to farnesol, farnesol is acyclic sesquiterpene alcohol. Acyclic means there is no ring. Sesquiterpene means 3 isoprene units, and alcohol means it contains 1 oxygen. So the molecular formula is C15H26O. So this is the structure of farnesol. So it is having 10 carbons in the chain, carrying 3 methyl substituents. At the end there is hydroxy, and there are 3 double bonds at 6, 2 and 10th positions. That is about the structures of gingiberine and farnesol. So what are the questions that are expected? You may be asked to write the structure and synthesis of gingiberine. Similarly, you may be asked to write the structure and synthesis of farnesol.